Today's afternoon session, titled Correlated Treatment of Many-Body Dynamics. Okay, before we start, I would like to once again strongly encourage you to participate in discussion, to ask questions, if possible, not by pasting them to the chat. Of course, it's a good way to do it, especially if you are shy or anything. But as Gabriele said in the morning session, it's sort of more natural that we speak, that we hear each other, that we see each other, and so on. Okay, anyways, feel free to raise your hand and you will be given opportunity to say your question out loud. Okay, so let's start with afternoon session. The first speaker of this session will be Professor Alexander Kuleff from the University of Heidelberg. And he will give us a talk titled Ultrafast Charge Migration in Molecules Initiated by Ionization and Excitation. Okay, Professor, the stage is yours. Feel free to share your screen and to start your presentation.
Okay, thank you. You see, I hope also my mouse, yeah? Can you hear me?
Yes. We can hear you loud and clear and we see your presentation.
Very well. Yeah, thanks. Of course, I would like to start thanking the organizers for inviting me to give this presentation and also for setting up such a wonderful program. I was really excited to see the other speakers and also the exciting morning session. So what I would like to talk about, and this is what I was also invited to do, to share a bit our experience in how one can treat coupled electron-nuclear dynamics. Of course, I will do it not in a technical mathematical way, would like to actually discuss an important physical mechanism or phenomenon that take place after ionization, and also we recently had some examples after excitation of a molecule, and this will be at the end of my talk. I mostly will concentrate on ionization. It's also historically how it was done, and since it's like a young scientist symposium, I would try to be as pedagogic as possible and not just to throw you nice pictures and numbers, but also to explain what stands behind. So that's why I would like to start with some basic quantum mechanics that we all know. So in order to have any sort of dynamics, any sort of evolution, a non-trivial evolution of a quantum system, what we need to do is actually to populate more than a single eigenstate of the system. So as shown here, if we have, let's say, a pulse which populates two quantum states with certain proportions, so what we create is actually a wave packet which evolves in time, and what we'll have in the case of these two states, we have the usual quantum beating. So the population will go back and forth and will jump between, in a sense, the two states. So this is, of course, irrespective of what type of quantum states are this. This will be, of course, the dynamics that we initiate. So it's clear that if we use short pulses for populating, for exciting our system and populating some quantum mechanical states, quantum states, we inevitably will trigger some sort of dynamics just because we will populate more than a single eigenstate of the system. So we will induce this type of quantum beatings. So this happens, of course, with any ultra-short pulses, and there were already examples shown this morning what kind of dynamics one can induce, and also even the charge migration was mentioned a couple of times. But before this, I would like to touch upon a very important issue, which actually is the electron correlation in the case of ionization and also in the case of excitation, which can, in a sense, play for us this game in populating several electronic states simultaneously or coherently in order to trigger the dynamics. And for now that the nuclei will be fixed, I will talk only about the electron, the pure electron dynamics. So we take a molecule, we fix the nuclei, and we compute the electronic states. In this case, the ionic states. If we do this with an independent particle model, so which means like Hartree-Fock or even with T and many others which don't take explicitly the correlation into account, what we will get if we compute the ionization spectrum of a molecule will be something like that. So we have ionic states which correspond to removal of an electron from a particular orbital. We can write this as the so-called one-hole configuration. So we create a hole in the occupation in the shells, in the occupied shells of the molecule, taking out an electron from a particular orbit. It's actually known for already many, many years that the electron correlation is very important in the process of ionization. So the electron not just goes away, it can also, because it's correlated with the other electrons and interacts, it can create additional states. Yeah. So what one can do if one takes the electron correlation into account and take the same molecule and compute the electronic spectrum, one will see a completely different picture. So certain states will be more or less the same, but just shifted in energy, which is not so important. But you will get additional states, which are like the one shown here, which are completely impossible to get with the independent particle picture model. So when we do ionization with independent particle picture model, one has to be aware that there are many states which are missing if we don't take the electron correlation into account. So for example, if we see like a spectrum like that, if we see that if we ionize from a molecule which is let's say here denoted in red, if we take out the electron from this particular orbital, we will populate coherently these two states, or the main state and the satellite, or the shake-up state as the experimentalists like to call it. So we will prepare an electronic wave packet which will inevitably evolve in time and of course induce some dynamics. Going deeper into the electronic shells, actually we can see this type of structures. So we will have a complete breakdown of the molecular orbital picture, and this is exactly what Alexei showed us this morning, the dynamics that one induces populating such kind of correlation bands. So there, in a sense, the notion of a particular state ceases to have meaning, and one really starts talking about correlation bands. So these are structures and effects which are completely due to the electron correlation. So in a sense, the electron correlation can do this job for us, in a sense, populating several states, even if we don't use ultra-short pulses, yeah, which embrace the states of interest. So this was actually conceived more than 20 years ago already by Lenz Ederbaum, and was called correlation-driven charge migration, so that the hole or that we create in the electronic cloud of the system, we'll see, can start to migrate just due to the fact that the electron correlation makes such that we populate more than a single electronic state of the system. Just to show you a few examples, just to have an idea about, let's say, what type of time scale we are talking about, what type of electronic motion or dynamics we're talking about. So we have many, many examples. These are typically, as I said, as we saw in the inner valence, where the after inner valence ionization, where the correlation effects are much stronger. So one can have, what is shown here is the Hall density. So this is the density of the Hall that one creates in the electronic cloud by ionization. And as I said, these are inner valence ionization. So we see for about a few femtoseconds, the charge can go from, the Hall can go from one side of the system to another. It can jump back and forth between jumping completely over the aromatic ring in this case for a few femtoseconds. It's not necessarily, of course, going from one end to another. You can have all types of breeding and so on, like in larger molecules, and also you can have these effects after ionization of the core, but this I will just mention here. Importantly, this is not always in the case of the inner valence ionization. So there are enough examples already where even after, or the correlation effects, electron correlation effects are strong enough that one has such kind of dynamics also after ionization of the highest molecular orbital, or the HOMO. So these are two shown here, and on one I will concentrate more later on the propiolic acid example. Just before moving, show you that, yeah, one of the experiments was already mentioned this morning by Henrik on such kind of electron dynamics. And so there was another one in the group of Francesca Calegari, also, which was one of the first in this, where such type of electron dynamics was observed. I don't want to touch upon these experiments, just want to say that the technology is there. So we have already the means to initiate and probe such kind of few femtosecond electron dynamics. Now, it's of course, the question is how we couple to the nuclear motion. Of course, if we stay only on the electronic space, these oscillations or whatever we induce will last forever. Of course, this is not the case, and the coupling to the nuclear motion, of course, makes such that one can trap the charge. And this is actually what makes it interesting also. Yeah? Just electron quantum beatings, okay, one can observe, but it's not, yeah, can be exciting, but it's not so practical and interesting at the end. So what makes it interesting is actually a lot in this field was initiated and motivated by a series of very important experiments done in the mid-90s by Schlack and Weinkauf, a number of peptide chains like this one shown here. So what they observed is that after ionization of the chromophore of the peptide, actually the charge goes to the remote end of the peptide, where into this amine end, and then the bond is broken on the other side. So we have really a chemistry of the system, and it was understood relatively shortly afterwards, or mostly at that time, that what is responsible for this type of dynamics and the bond breaking here is actually the charge indeed has to move and to break the bond. So it's not just transfer of energy to vibrational motion. This is not enough to break the bond here. So really the charge has to go there. And so this was called charge-directed reactivity, actually a seminal paper by Françoise Remacle, who will talk at the end of this session. So the charge-directed reactivity, when yeah, there drove a lot of interest, and okay, this is, I forgot that I put another example. This is another example of experiments of Schlack and Weinkauf in a smaller system, where they see basically the same. So you ionize the chromophore, the charge goes to the amine end of the system, and this bond is broken, and they measured some sort of like the time of this charge transfer and bond breaking together. Anyway, what I wanted to say is that it brought us, and not only us, many people had this idea that because due to the coupling between the electron, or non-adiabatic effects, the coupling between the electronic and the nuclear motion, if we are able to control this pure electron dynamics, one might steer afterwards the chemical reactivity. It is intuitively clear that if we, let's say, being able to place or to localize the charge in the particular places of the molecule, we can of course induce, this is a charge, the nuclei are also charged particle, and they interact with this charge. So we will be able to initiate some sort of dynamics. We did also some work on how one can control, or whether one can control this pure electron dynamics, and still only on the electron dynamics. The nuclei will not moving, we'll start moving them now. And we saw that actually it's possible to do things like that. This is a very similar system to the one, the penna. It's just that the chromophore is different, the rest is the same. So we see that by ionizing the HOMO orbital of this molecule, you induce this very fast charge migration. One can design pulses which can stop the charge, let's say in the remote site, in the amine site, which means in a sense speed up the dissociation, or keep the charge on the chromophore, which will in a sense hinder the dissociation of the molecule. So we control really the chemistry of the chemical reactivity of the system. Now, of course, in order to do such kind of control, we need some time. So these pulses, irrespective how one design pulses, one needs a few femtoseconds probably to be able to control, and also, of course, for observation of such kind of effects, we need that these electronic coherences last a bit longer. And here, this is a figure that I borrowed from this paper of Oriol and Robin Santra, where they pose this question, and one can understand why the nuclear motion or the coupling to the nuclear motion may induce the decoherence in the charge migration. And it, of course, depends very much on the topology of the populated states. So if they are running parallel, actually you won't induce decoherence, or very little. If they have a very different topology, of course, the wave packets, the nuclear wave packets will start moving apart, and this will, of course, induce decoherence and of the charge migration also. So they did some studies on, they took a water molecule, they took some states of the water molecule and all the vibrational modes of the water molecule, and actually saw that in this particular case, the decoherence or the time window during which you can talk about that something electronically might jump and have a quantum beatings is actually extremely short. So in this case, they saw something like 1-2 femtoseconds. There was another series of, one of the first who actually studied this phenomenon, or how the nuclear motion will eventually destroy or will enter the pure electronic coherence. It was Morgan Bachet and a group of Mike Robb at that time. They had a series of molecules where they did a coupled electron-nuclear dynamics, sometimes quasi-classically, and they had also a pure quantum calculation showing that, again, in some certain cases, in certain states, when you populate certain states, this decoherence can be really fast. So we're talking about 1-2 femtoseconds, which of course poses the question, is the decoherence, so the charge migration, the electron coherence that one creates at the beginning, always so fast, so by the nuclear motion, so which will mean that this idea or the dream of atochemistry that one can control nuclear dynamics or chemistry of the system by talking only to the electrons or playing with the electron coherences, better to say, is not possible, just because we don't have so much time to influence the electrons and before the coherence is gone. Now, in order to do that, it's of course, because we're talking about coherences and phases and so on, this is, it's important that one does everything quantum mechanically. Also, the coupling between the electron and nuclear dynamics is taken quantum mechanically. And as I said, since it's a young scientist meeting, I will spend a few minutes to describe how one can do that and how we did that before showing you some results. So one of the way, and this is by far not the only one to do coupled electron-nuclear dynamics, and I'm sure we'll hear later in the session other approaches. One is to start from taking the molecular wave function and do the so-called Born-Hwang expansion, so to use the electronic states as a basis, and these will be our nuclear wave packets which are moving on these states. So the electronic states, of course, is a result of solving the electronic time-independent Schrödinger equation, which one can do with any electronic structure method or preferred one. As I said, important is, if, depending on, of course, what type of dynamics and which part we want to look, but taking proper account of the electron correlation is always necessary. So when one constructs, and doing this first step, constructing the potential energy surfaces, it's good that this is done with a high-level post-Hartree-Fock method. Now, of course, if we do that and we take this wave function and put it in the time-dependent Schrödinger equation, what we will get at the end is something which has these nasty terms here, so-called non-adiabatic or derivative couplings. So these are coming from the kinetic energy of the nuclei, which is acting on our electronic states, which depend also on the nuclear coordinate. So it's very, very difficult to solve this equation and compute these derivatives at each point. So what one does usually is some sort of diabatization. So we try to transform to a basis, to a diabatic basis, because this is the adiabatic one, which you get from the electronic structure, and shift the derivative couplings to a potential energy coupling. So then your potential energy is non-diagonal. You have couplings between the electronic states, so you can transfer population, but otherwise you can propagate normally within the kinetic energy operator is, the kinetic energy operator is diagonal representation. So again, there are different ways to do diabatization. So what we used is so-called Webronic coupling model, which was proposed also many years ago. You can find more information in this paper of Lenz and Horst. The idea is that one uses an expansion, a Taylor expansion of the potentials, and which are nearly harmonic in this case, and you have some sort of linear or quadratic or whatever bilinear coupling. You can have different coupling schemes between the states and construct a Hamiltonian in which already you can solve the time-dependent Schrödinger equation with this Webronic coupling Hamiltonian and propagate your states. In this case, you have a superposition of electronic states, so you populate simultaneously several electronic states and put a vibrational wave packet on them, and this you have to propagate in this non-adiabatically coupled states, meaning you transfer population between the states and during the wave packet propagation on them. So this is the third step, and this, since we're in Heidelberg, we do this with the NCTDH, or the multi-configurational time-dependent Hartree approach and program, and you can find information on the website here if you're interested. So there is a last point in order to be able to analyze and to look again on these electronic densities that we tend to show in this case. If you take the full molecular function, then also your electronic wave function will depend on the nuclear coordinates. So you can integrate over the electronic coordinates, but you will have a complicated object like that. So what is important to use is, again, to use the diabatic representation, where in principle the states depend very little, or ideally not, from the nuclear position. So you can factorize this expression into purely electronic part that you can study. And then this is the overlap between the nuclear wave packets which are running on the diabatic states. So this is how one can construct the electronic density. So we did this for the charge migration in propiolic acid. This is how the spectrum, or the outer valence part of the spectrum, looks like in the fixed nuclei. if you ionize the HOMO, which is on this triple carbon-carbon triple bond, you get oscillation between these triple bonds and the oxygen here. So this is a few femtosecond oscillations that one get. So we compute these states for those who are interested with the Green's function methodology. So this is so-called ADC3, third order perturbation theory. We took all 15 normal modes of the system, constructed the vibronic coupling Hamiltonian, which takes all those 4 states into account in all degrees of freedom, all 15. This is how the other points are the adiabatic states, and of course these solid lines are the constructed vibronic coupling Hamiltonian model. So then we took the initial wave packet, constructed such that it corresponds to the ionization of the HOMO orbital, the blue one here. This is what we got. So as you see, as I mentioned, the overlap between the wave packets running on potential surfaces are sort of a measure for the coherence or the off-diagonal parts, or the overlap between the nuclear wave packets running on the two of the states, 1 and 3 in this case, is sort of a measure of the coherence of the system. So this is what is shown here, that the decoherence due to the nuclear motion takes place for about, let's say, 15 femtoseconds. So it's long enough. This is how the charge oscillation will look if you take into account also the coupled electron-nuclear motion. So we see the charge is again, or the whole is localized on the carbon triple bond. It goes to the oxygen back and forth, and then it's actually trapped, more or less delocalized over the system due to the nuclear motion. But anyway, the charge makes a few oscillations before it's get trapped. Now, just a few words how one can, let's say, measure this. It was mentioned already this morning. There were talks on transient absorption. So we had also this idea that one can do transient absorption in this particular case. So these are the core states. This is the oxygen KH, the 2 oxygens here. These are the 2 carbons. The difference here is very little. It's just blown up. They are nearly on top of each other, but it's a chemical shift of the 2 carbons on the triple bond. And then one can drive transitions between the KH, or the 1s of the carbon, to this valence part of the spectrum. We did this transient absorption calculation, and sees that if you do it from the carbon, or if you do it from the oxygen, these are the 2 oxygens and the 4 lines, because you have 2 states which you drive transitions to. So one sees that it's not only that you get the oscillations, and this was important for us to check that it's not only that the time scale of the oscillations are there, but also one can have sensitivity on the position. So if you see there that you start from the carbons at the beginning, and then the charge goes to the oxygen, and then goes back, of course, in order to do such kind of measurements, you have to be able to cover both 300 and 500 eV range in order to see this oscillation, but at least this is possible doing the transient absorption. Now, as I started, it actually doesn't matter what type of states you populate coherently. You will induce some sort of dynamics. And you don't need to ionize, you can excite. This was actually, which we had this idea a long time ago, and Tony Dutoy did first works on this type of charge migration following excitation of a system. There it's actually much more, not much more, but it's also very interesting. It's more complicated because you have migration both of the hole that you create and the electron that you put, so both the electron and the hole and the particle can move. They can move together along, or they can move in different directions, as in this example, which Tony studied some time ago. Interestingly, Tony was one of the first who proposed to use transient absorption spectroscopy to trace charge migration in these two works. Let me show you an example which we recently have. I hope I have a few minutes. I'm nearly finished. Just want to show you an example of charge migration following excitation. And this is something which an experiment done by Hans-Jakob Wörner and by Dan Matsuliak at ETH Zurich. So they took a silane molecule and they used an intense infrared pulse for exciting the molecule, and then an X-ray probe or transient absorption to probe the dynamics. So this is the traces that they got. So what I will concentrate, they see also, of course, ionization, and there's a lot of interesting things also there. But I will concentrate on this part. What they see is some sort of quantum beatings, which dephase for about, let's say, 10 femtoseconds, and then reappears, or you have a recurrence after 40, 50 femtoseconds. If you analyze this type of quantum beatings, which you see also here, and you do a Fourier analysis, you see that actually you have two beating periods. So one is like 1.4 femtoseconds, which is gives you a single signal here, and another one with 1.3 femtoseconds, which actually appears a bit later. Yeah, so this is something that the analysis can show us, and one sees also that the coherence is between mainly two states. So our analysis showed that it's mainly between two states. What is B, which is the first bright state, first bright excited state of the system, and the high-lying what we call C. So this is a Rydberg state of the silicon. Then we have also an initially dark state, A, which will take also place in the dynamics. So what we did, we constructed potential energy surfaces, constructed Weberonic coupling Hamiltonian, 15 states taken into account, and we did the non-adiabatic dynamics, as I showed you for the ionization case. So what we see, and it fits again very well to the experimental observations and to all kinds of analysis that one could do with the experimental data. We see the following. So although with the intense infrared and this multi-photon excitation, one actually populates a large number of states. Mainly what survives and what gives the coherence is, or these coherence beatings, is the two states, as I mentioned. So this decoherence goes, as I said, for about 10 femtoseconds. And then you have a revival. So these are our calculation, what our calculation gives. Then you have a revival of around 50 femtoseconds in our calculation, a bit later than what they measure. What is important is that another coherence grows up and appears a few femtoseconds later in very good agreement with what experimentally is seen. And this is the coherence between the state A and the state C. So the mechanism is actually the following, and this is also what all our analysis and simulations show, that we create a coherence between these two states here, which starts evolving in time. The wave packets start to evolve, and then days after about 7 femtoseconds needs that for the wave packet to go through set of conical intersections to the A state, to this initially dark state, and to actually establish a new coherence between this new this A state and the higher lying Rydberg state on the silicon atom, and to continue having these also recurrences more or less at the same time as the other wave packet, and it's responsible for the second beating period. One can, of course, do some analysis of what the density is doing, what the Hall and the particle. It's actually very difficult to visualize here and to understand, and I don't have much time to explain. But this is something that these are results which we are very excited from. So with this, I would like to conclude. So I hope you got a bit of an idea of what the charge migration as a phenomenon and mechanism is, and following ionization or excitation can be a very efficient actually way to redistribute the charge in the system. So this is something which can move charge and distribute it along the backbone of the molecule, and then when the nuclear dynamics kicks on, to trap this charge. So the second, which I would like to mention, is that in principle, long-lived coherences, electronic coherences, can exist in polyatomic. So we have examples, we have other examples already with other molecules where we see longer lived. It's not necessary that the nuclear motion will always destroy the electron coherences for just a few femtoseconds. And the third is, this is also very important for me, and it was in a sense what I liked very much with these Silane experiments and our calculation, is that actually a passage through a conical intersection is not necessarily, doesn't necessarily destroy the electron coherences, which was what we believed at the beginning. We can actually create new ones. So we see that even after passing through the conical intersection, we can establish a coherence with the higher lying states. And would like to end up a bit, on the bright side. So I think that the dream of atochemistry might soon become a reality. We have already all prerequisites to doing that, both technically, on an experimental point of view, and also theoretically. We can already deal with not so small systems and understand complicated dynamics and analyze. And by thanking, of course, the people who were involved and did most of the job, is, of course, on the theory side, my former PhD student, Nikolai Kuleff, now at EPFL Lausanne, and my postdoc, Victor Debray, who's still with me, and some other people with whom I collaborated and whose results I also showed. Of course, Lenz is always around and ready to discuss interesting physics, and on the experimental side, really a wonderful collaboration that we had now with Hans Jakob and Danilo Mazulek from ETH Zurich. And of course, thanks to you for your kind attention.
Hey, thank you, Professor Kuleff, very much, and really nice and I would say educative talk. Okay, the session is now open for discussion. While we are waiting for some brave hands, I will give you a virtual applause.
Thank you. Yeah, sure. I also encourage.
Okay, we have risen hand.
Yeah.
Hi.
Hey, Morgan.
Yes.
Nice to see you.
Yes, thank you for the talk. Nice talk, nice results. I just have a very short technical question. In the last result that you showed, so the pump was an infrared.
Yes.
So it was a multi-photon excitation.
Yes. Yeah.
Yes. And do you take that into account when you calculate the initial weight?
We tried. Yes, we tried. And we did all kinds of we tried many different methods to do that and to see what is actually the initial population by this multiphoton ionization. And what we got is that in principle, you populate nearly everything. Yeah, so it's you need something 6-7 photons, and you can imagine with 6-7 photons and all the widths, you have a very broadband actually really populates everything, and the difference in the population is relatively small. So in the propagation, we usually took an equal population, because at the end, this is not really important for neither for the oscillation, nor it's just when we constructed or reconstructed, because we also did a reconstruction of the transient absorption spectrum. There it's just that the contrast or the intensity of the different lines might be different, but the population, the initial population doesn't really change the dynamics that we observe. And even if you start with all these states populated here, which is the case, actually due to conical intersections, which are nearly everywhere, you very fast transfer the population more or less only to the two lower states, which are important. And this is a Rydberg state over there. It's very weakly coupled to anything else. So whatever you put there, it stays there. So that's why the coherence is between these Rydberg states and some low-lying states, but the two lowest lying states are the one which survive. This is what we got from many actually tests in different configurations.
Okay, thank you.
Okay, we have another more question from Professor
Remacle. Hello, Alex.
Hello, nice. Françoise. Nice to see you.
I appreciate. Let me put. I have a question about the normal modes you included. Which one are they?
In this, you mean in the C-line?
Yeah, in the same result.
Yeah, we didn't take all. So these are, let me think. So these are the three degenerate E1, if I'm not mistaken. And non-symmetric stretch, which we have.
Okay, so there is no Lanteller. You don't need the T2 or.
Oh, no, we did. What we have, we took the faster ones. Is that it was very difficult to construct a good vibronic coupling model. Because of course 4 modes is nothing, but the point was with the vibronic coupling model that we took. So we took the fast modes, and the slower ones are not taken into account.
Yeah.
And at least what we tried is that they are not really important for this particular dynamics that we see. And the fact we have a very good agreement without fitting anything with experiment was at least for us was reassuring that we are not doing much harm by excluding a few of the modes. Yeah.
Thanks.
Yeah. Welcome.
Okay, we have one more question in the chat. So Torsha asks, did you have to use ADC3?
We did for everything what I presented in the ionization part, in a sense, in the charge migration, is done with ADC3. Yeah, so this is how we do ionic states here in
Okay. So,
in this particular case, for the excitation, we used EOM CCSD, and this is the basis set. What we
I see. I actually wanted to ask. Sorry, I interrupted you.
No, it's fine.
Okay, I actually wanted to
do ADC2. We did ADC2, but for certain things we prefer to do EOM in this case.
Okay, according to my poor experience, one needs multi-reference treatment actually of chemical states usually.
You're correct. In this particular
ADC3 is okay. So
yeah, in cases where you have, let's say, large amplitude motion and where you have dissociation, where you will most likely you will need multi-reference. In the cases for propiolic or whatever, where indeed the potentials are very bound and the system is very rigid and stable, does have vibrations, it's perfectly okay to use a single reference.
Okay. One more, Professor Kuleff, for really nice talk, and now we have to go on with our.
Okay. Yeah. Thank you. Yeah.
Our next speaker is Thierry Tran from the University College of London, and he will give us a talk titled Simulation of Coherent Control of Electron-Nuclear Dynamics with Quantum-Ehrenfest. Thierry, the stage is yours.
Okay.
Feel free to share your screen.
I'll just try to share my screen.
We can hear you, we can see you.
Can you see the slides?
Yes, perfect.
Well, I can't see them on my screen, but oh, perfect. Is it working now? Yes.
Yes, we can see.
Okay. Well, first of all, I would like to thank the committee for giving me that opportunity to be able to present my work in the symposium. So the motivation for my work is that it is known from attosecond spectroscopy that the pump pulse that originate from source such as a high harmonic generation of free electron laser source, that they often, first of all, photoionize the molecule, and due to the small band, the large bandwidth of the energy, because it's a very short pulse, we often end up ionizing multiple states. So we end up creating a coherent superposition of electronic state. And there's been a recent work where they have shown that they could also control the dynamics after the pump pulse with the help of a probe pulse or control pulse, by either playing with the time delay of the pulse or by changing the carrier phase envelope of the pulse, and with that they could change the outcome of the dynamics. For the next few slides, I will give a short overview of the method I'm employing for my work. So on that slide, you can see non-exhaustive list of available methods for non-adiabatic dynamics that you could find in the literature, that range from all the on-the-fly method, where we use either trajectory-based dynamics, such as in Thierry surface hopping dynamics or classical Ehrenfest dynamics, or using a Gaussian basis function for methods such as initial multiple spawning, and then with a quantum trajectory where we have interacting basis function in direct dynamics, variational multi-configuration Gaussian, and the Quantum-Ehrenfest method, which it is based on. Other method that has already been mentioned in previous talk, such as the MCTH method, where the potential energy surface is fitted beforehand, and then they run the dynamics on this fitted potential energy surface. So the DDVMCG method is obtained by solving the time-dependent Schrödinger equation by having a quantum treatment of both the electron and the nuclei at the same time, and we obtain a variational solution of the time-dependent Schrödinger equation. And as I mentioned before, the potential energy surface for that method is computed on the fly. In the DDVMCG method, the ansatz we use for the representation of the nuclear wave function is by expanding the nuclear wave function into the linear combination of Gaussian wave function with each their own expansion coefficient A. And also the important part is that different component of the Gaussian wave function are time dependent, such as the width, the momentum, and the position of the center of the Gaussian wave packet. And when we apply them, when we try to get the variational solution out of this time-dependent Schrödinger equation, we obtain equation of motion for both the expansion coefficient and also equation of motion for the Gaussian parameter. So the important bits in DTV-MCG is that in the obtention of the equation of motion, we expand the nuclear Hamiltonian up to the second order. Also, we do a local harmonic approximation around the center of the Gaussian wave packet. So we need the energy, the gradient, and the Hessian. So now on that slide, I will just quickly go through the Quantum-Ehrenfest method. So the Quantum-Ehrenfest method uses a single frame as DDV-MCG for the propagation of the nuclear wave packet. The important bit is that each new basis function only see technically only one time-dependent potential energy surface. In order to derive the equation of motion for the Quantum-Ehrenfest method, we start the derivation from the exact factorization. And in that method, we represent the electronic basis into in the diabatic basis. So our electronic wave function is a linear combination of diabatic electronic wave function, and we yield that equation of motion for the different coefficient in the diabatic representation. And the electronic wave packet is propagated directly within the electronic structure method. And there's some nuclear dynamics driver that is in the quantic software that is used for DDV-MCG only see one potential energy surface. And also another thing that is important about the method we have been working on is that because we also want to be able to reproduce some of the experimental results where they have achieved up to a certain extent a control with a control or probe pulse, we also have implemented the pulse inside of the electronic structure method for the Quantum-Ehrenfest propagation. And the way we have done it is that we have implemented the dipole electric integrals directly within the one electron operator for the electronic Hamiltonian. So I can switch. Seems that my presentation is a bit stuck. Okay. So the electronic structure method I'm using for my work is based on the CAS-SCF approach. So for the Quantum-Ehrenfest part, we use the CAS-CI approach, and the way CAS-SCF, CAS-CI work is that we define a certain set of orbitals in our active space, and then we generate all the configuration state function by putting all the electrons in the different possible orbitals. And with that kind of method, we can capture most of the static correlation and also include a bit of the dynamic correlation, depending on how we play with the active space. The dynamic correlation can also be included by using a perturbation correction with methods such as CAS-PT2. But for my work, we mostly focus on the CAS-CI approach. So in the result we get for our dynamic simulated on Quantum-Ehrenfest, also the effect of the pulse in order to control to a certain extent the dynamics, there is some theoretical consideration to have. First is that it is known in the case of two-state electron system that the general solution for two-state system can be written as a linear combination of both. And in the previous talk, it has been shown that you can observe this oscillatory behavior. You will have population being exchanged between the two states. And usually the oscillation period depends here on the energy difference between the state. And if the energy difference go close to zero, so when you reach a region of degeneracy, such as a conical intersection, you often observe collapse in the electron dynamics. Another theoretical consideration to have is about symmetry rules. Often for describing conical intersection on molecular systems that has a high level of symmetry, we can often determine already which degrees of freedom will be necessary in order to be able to describe the potential energy surface important for the non-adiabatic events. And the short version of it is basically that if we have two electronic states of a certain symmetry, we need a nuclear motion to be of that specific symmetry, and the product between the two of them should give us a totally symmetric representation. And the thing is that when we generate a superposition of state, we end up initially with an electronic wave function that has already a specific symmetric character, and it's potentially possible to be able to observe non-adiabatic events even outside of conical intersection. And this is something I will show with a few molecules we have worked on using the Quantum-Ehrenfest method. So the first example will be with protonated shift base, where the aim was to control the bond length alternation by playing with the superposition of state, where we start from a ground state and then we excite it either on the first excited state or second excited state. And we know what is a valence bond representation of these two states and the kind of character, and also how the potential surface looks like, and where the conical intersection is located. And we know that, for example, if we want to reach a conical intersection where we have the isolation happening for that system, we must observe a bond length alternation. If we excite directly from the S1 state, we know that we'll reach a conical intersection with the S2 state, and some population transfer should occur. And then it can reach the conical intersection with the S0 state. But another way of achieving this is also by creating the superposition already at the front quantum point. And in the results that you can see on that slide is that we have control the bond length alternation by, like I say, creating the superposition already at the front quantum at time 0, so at the front quantum point. And we can see that we have a different behavior in the nuclear dynamics. So we can control to a certain extent the nuclear dynamics by playing with the initial electronic wave function. Another example I can use also, and that is also richer in terms of symmetry, is a benzene cation. There was some MCTTH simulation on the benzene cation where they have involved 8 states in the dynamics. So you can see all the different states in that slide, as all the 8 states and the symmetry level. And our aim for that project was to be able to see if we could control the nuclear dynamics and steer it in a specific direction by playing with the initial superposition of state and by taking some of the state with specific symmetries. And here I'm showing 2 examples where we have done it with a 3-state superposition and a 4-state superposition. And from that point, we can see that we have, well, first of all, extremely different nuclear dynamics. Due to the constraint of time, I won't be able to show the full symmetry analysis, but for that work, we have been able to predict already at the beginning, based on the state we included in our superposition, what the initial gradient and in which direction the nuclear dynamic will be driven based on this symmetry rules that we observe usually at conical intersection. And this kind of things has been observed in our dynamics, even outside of conical intersection at the front quantum point, where the different states are well separated in energy. Last example I will be presenting is Alin cation, where here we wanted to control the dynamics after exciting it to a specific superposition state by the aim of a pulse. And here we started the dynamics for the Alin cation on a superposition of D0 and D1 state with a 50-50 composition. And we then came with a infrared probe pulse that you can see at the bottom in blue by the blue envelope. So first thing that is interesting to notice is that in the spin density, when we hit the conical intersection for that system, we see that we have a collapse in the electron dynamics. We no longer see this charge oscillation for a short amount of time. And that thing is directly translated into how the nuclear dynamics evolve. We can see that the two CC bond length start to evolve in a different way, depending on if we put a pulse or not, despite having at the end up on the same final state where we see in both in the dynamic with pulse and without pulse that we have mostly D-naught, most of the electronic wave function on the D-naught state. So in conclusion, is that the electronic coherence play a very important role in the initial nuclear motion, even if it is known from the literature that some the electronic coherence can have a very short lifetime. It can already play an effect in the nuclear dynamics by first, if we choose carefully the superposition of state we want at the beginning, we can steer the nuclear dynamics in one specific direction. So by using symmetry rules, we can already determine in which direction the dynamics will go through. And most importantly is that we can observe conical intersection-like dynamics outside of this region of degeneracy. And of course, one of the main goals of the simulation here is to be able to see if we can control the nuclear dynamics by choosing a specific superposition state by playing with the phase between the state and the mixing ratio. And also how with a pulse we can control and maybe steer the dynamic and basically achieve perfect control chemistry of our system. So I would like to thank both my supervisors, so Professor Graham, as well as a group of Professor Graham Worf, as well as Professor Mike Robb from all the guidance. Okay. That's all from the talk.
Okay, thank you very much, Thierry, for a really nice talk. We have some time for at least one question. So the session is open for discussion. While we are waiting, just a quick question. So if I understood correctly, Quantum-Ehrenfest can be done in the full dimensionality.
Yes, it can be done in the full dimensionality.
Okay. Just like variational Gaussians, right?
Yes, I mean it's based on DDVMCG.
Yeah, okay.
It's just that in DDVMCG you have the option of freezing some degrees of freedom. In the benzene cation work, we have frozen some degrees of freedom because how many degrees of freedom we get with benzene? 42, I think, maybe.
Something like that, yeah.
Yeah, so we have frozen a few degrees of freedom in order to just look at the most relevant one, and also to make it less expensive, because if we go in full dimensionality, we need more Gaussian wave packet in order to reach convergence for the results.
Okay, thanks. Okay, do we have anything in chat? No? Okay, if there are no questions, Thierry, thank you once more. And now we have a coffee break on the schedule. So see you back here in 20 minutes. So we will proceed in 15:40. Okay, I think it is time to proceed with the session. Hello to everyone once again. So our next speaker in today's afternoon session will be Mr. Jasper Peschel. I apologize if I mispronounced your name or surname, sorry, in advance, from the Lund University, and he will give us a talk, Complete Characterization of Multi-Channel Single Photon Ionization. Jasper, the stage is yours.
Perfect, thanks a lot. Thanks for having me here. Yes, my name is Jasper. I'm a PhD student at the Lund University. I'm working at what we call the intense XUV beamline, which is part of the Lund Laser Center. I'm sorry, and the beamline is actually aimed towards generating intense high-order harmonics, with the aim to do pump-probe experiments on molecules. However, along the way, we did some studies on photoionization, and I think they're quite interesting and worth presenting to all of you. So let me get a pointer. Yes, let's look at photoionization. So generally a photon excites an electron from a ground state into a continuum state. The whole process can be characterized by a dipole matrix element which usually carries an amplitude and a phase. The amplitude usually can be described by an angular coefficient and a radial phase, a radial amplitude. The phase consists of a contribution coming from the atomic system as well as a contribution from the photon. Now, how can we detect these electrons? So how can we access this matrix element? One thing we can do is we can measure the yield of the outgoing electron. We can do that using various frequencies. In our case, using high order harmonic generation, that's quite handy because it's intrinsic to the process. We can measure the different yields as a function of the kinetic energy. However, in any case, we can mostly only access the modulus square of the matrix elements, which is why we have to use a slightly different technique. In our case, we use a two-photon interferometry technique to probe the phase. Here we add a second photon, which further excites the electron to a so-called sideband. This can happen via two different pathways, an absorption and an emission pathway. And this adds another dimension to the detection scheme, which is the delay between the two pulses, which ultimately leads to the yield of the sideband oscillating. However, we want to study single photon ionization. We're only using this scheme in order to access the phase of the matrix element. Let's take one step back to single photon ionization. We know that if, for example, if we start from a p ground state, we know that by selection rules, these the angular momentum p of the ground state changes either to s or to d, so plus or minus 1. And usually we are also not able to access these two different channels. What we do know, however, is that the electrons released into these two different channels are characterized by the spherical harmonics, which are different for different angular momenta. So what we have to add, in addition to our second photon to the measurement scheme, is angular resolution. So what we ultimately end up with is an two-photon interferometry experiment, which is angularly resolved. In this example, now I show you starting from a p ground state, which can be neon or argon, for example. In our case, we conducted the whole experiment in neon, but I'll show you later that this is also quite universal. In our case, the detection scheme, the two-photon interferometry, we use Rabbit, but in principle, the phase can also be accessed by other two-photon interferometry methods like streaking, for example. Let's look a bit into the numbers. So what do we have to do in order to access the matrix elements? We know that the sideband signal, the angle and delay dependent sideband signal, consists of a superposition between the absorption and the emission pathway, as well as the different angular momentum channels. Each of the channels is characterized by a matrix element, which again depends on the angular momenta of the ground state, the intermediate state, which we call lambda, and the final state, which we call L. This is the experimental setup that we used for the experiment. We call it the intense XUV beamline. In Lund, we start with a 800 nanometer titanium sapphire laser providing 10 Hertz, 50 millijoule and 40 femtoseconds. We loosely focus the IR beam over 8.7 meters into our generation chamber with the aim to generate high intensities in the XUV range. We then recently have implemented our new online XUV IR interferometer. Here we make use of the different divergence between infrared and XUV beam. We use a Holy mirror, which reflects the outer part of the infrared beam into the infrared arm, where we have a translation stage to introduce a delay between the XUV and the IR arm. In the IR arm, we use an aluminum filter to block the residual infrared, but also to shape the XUV spectrum. Second Holy mirror is used then to recombine the two beams collinearly. Further, we focus the we focus the beam into our application chamber using 2 toroidal mirrors in a water-like configuration. And here we are able to detect electrons and ions with our double-sided velocity map imaging spectrometer. However, in this experiment, we only use the electron side. This is the electron momentum map that we gain from the VMI detection. Let's look into the photoelectron spectrum. Here I show you the photoelectron energy plotted as a function of the delay. We see that we get contributions from absorption of the harmonic orders. And in between, we see the sidebands. If the delay changes, these sidebands, they oscillate out of phase with the oscillation seen in the harmonic contributions. If we now integrate over all the angles, and I instead show you the we integrate over all delays, and I instead show you the emission angle, we see that, again, we see the harmonics and the sidebands. And here the contributions from the absorption of different harmonics leads to a superposition of S and D waves, whereas the sidebands consist of P and F waves. Now we want to quantify this a bit further. How do we do that? We take the sideband signal as a function of angle and delay, and we decompose it in an expansion of even Legendre polynomials up to the 4th order. We then gate the different sidebands, and we do a fit of this function to the sideband for each of the delays. Like this, we get the delay dependence of each of these components, H0, H2, and H4, as you can see down here. And we see that they are oscillating, which means that they carry, each of them carries a mean value, an amplitude, and a phase. That gives us in total 9 observables that we can extract from this data. Let's jump back now to photoionization. We remember that the sideband signal, the one that we just measured, consists of this superposition, different angular momentum channels, absorption and emission pathway. Now let's introduce the matrix element for the 2-photon transition. So we again have an angular coefficient, we have a radial amplitude, 2-photon amplitude, and we have 3 different phase contributions. These 3 different phase contributions correspond to the contribution from the continuum phase, the 1-photon phase, so from the ground state to the intermediate state, and from the harmonic phase, which is a contribution from the harmonic beam from the photons. Again, just a reminder, we only want to extract the 1-photon phase because this is what we want to study. However, in total, we have, if we add up all the different angular momentum channels as well as the absorption and emission pathway, we end up with a total of 12 unknowns. However, we remember we can only extract 9 observables, so we have to look into this these different contributions more closely. What we did in Lund then is to focus on the continuum transition. So in this case, I only show you now the transition from P to D, and then in particular, the difference between the D to P and D to F transition. What we found is that these can be correlated by a constant alpha, and in particular, the 2-photon amplitudes can be correlated by this alpha. If we compute this alpha using angular channel resolved many-body perturbation theory, we get an energy dependence, as you can see here. We did this in neon. Then we did the same thing in argon. Looks pretty much the same. We did the same thing in helium and in krypton. What we can identify now is that this alpha does not depend on the atom. It only depends on the intermediate state lambda. This is very nice because that means there's some universality to this property. Further, we also compute the different phases of the continuum transition. Again, I show you the results for all these different atoms. And again, we see that the phase is equal for all these different intermediate states and different atomic systems. Now I show you the phase for increasing angular momentum for the absorption pathway. However, this is true for the emission pathway as well as for the case of decreasing angular momentum. So also here the phase seems to be independent of the atom, which means it's universal. So we go back to our quantities, and we now, if we use this universality, we now reduce the number of unknowns to 9 parameters. That's good, because we know we can measure 9 observables from the experiment. So the last thing we have to do is compare this equation with that equation, meaning we do a global fit of the 9 unknown parameters in this equation to our measured observables. The result of the fit is shown here as the red curve for the H2, H0, and H4 coefficients. That means now we get values for the different phase contributions and the amplitudes. If we do this now for all the different sidebands, we get an energy, we get this energy resolved. Now here I show you the results of the single photon phases for the S emission and the D emission. So from P to S and P to D. We first see that both of them increase with energy. We see that there's a difference of roughly pi between them, a phase shift. And now if we go back into our atomic physics textbooks, we know that these phases, they consist of a Coulomb phase, a contribution from the short range potential, and a contribution from the centrifugal potential. Let's plot this as well. I show you here now that the dashed lines are the Coulomb phases, again for D and for S. And now we look at the quantum defect for the S waves, and we see that the short range potential gives a contribution of roughly 1.2 pi, which moves the pure Coulomb phase exactly where we have our measured values. And what I forgot to mention is that this solid line are calculated values using the same method as I presented you before. We don't get a contribution of the centrifugal potential for the S waves. However, for the D wave, we get mostly pretty much only a contribution of the centrifugal potential, whereas the short range potential is almost 0 for the D wave. So now we have characterized our single photon phases, and now we can go back to our single photon experiment, and using these phases now, we are able to also extract the single photon amplitudes, where we don't do a rapid experiment, but we just take one XeV photon, we ionize, and we measure the angular dependence. Here I show you now the ratio between the single photon radial amplitude for the P to S and the P to D channels. And we see that we are in good agreement with Feinholz's propensity rule, as all of these are above 1. To conclude, we are using angular resolved rabbit, and we are able to extract the channel resolved phases and amplitudes, which then fully characterizes the electron wave packets, meaning we fully characterize the single photon ionization in neon. Yes, and at the end, I would like to thank all the collaborators in Lund and in Stockholm that helped me conduct this work. Thanks a lot.
Okay, thank you, Jasper, and really nice talk. So the session is now open for discussion. Feel free to raise your hand if you have any question or comment for Jasper. Okay, while we are waiting, just a brief question. Can you do these types of measurements on the molecular systems?
Very good question. Of course, we discussed this, and we would be very happy to do that. What we have to study first, a bit more in detail, is the continuum transition in the environment of a molecule, because of course the continuum is more complex in molecules.
Sure.
But as soon as we understand the continuum transition more, I'm very optimistic that this would give equally nice results. Yes.
Okay. Thank you. Any question? I don't see any question in chat. No hand is risen. Okay, then thank you, Jasper, once again for your nice talk. And we proceed with our session. So the next speaker will be Bruno Tenorio from Technical University of Denmark, and he will give us a talk, multi-reference approach to the computation of double core Hall spectra. Bruno, feel free to start.
Okay, thank you so much for the introduction. Let me see. So you see my screen?
Yes, yes, we can see it.
Okay, so good. Sorry. Yes, so thanks for the opportunity of presenting here. So I'm Bruno Tenorio, I'm a postdoc at DTU. My supervisor here is Sonia Coriani. And today I will show my recent advances and, let's say, adventures by developing multi-reference methods for the computational double core hole spectra. Okay, so by double core hole spectra, I mean the single site double core hole, which means that the double core is on one atom, it's on the same atom, because you can have multi-core and scattering in a molecule. But okay, the single site double core hole is the most interesting one. And of course, I will present my results from different implementations targeting at the pre-edge and the post-edge regions. So the double core hole, as well as in the single core hole, you can split the spectra in the pre-edge and the post-edge regions. And normally, as in the single core hole, we have different approximation for each region. So I'm aiming at targeting the two of them with different approximation, but within the multi-reference approaches. But before I show you my developments and my results, let's see what's interesting about double core hole. Why should one spend time studying double core hole? Well, the single site double core hole spectroscopy is known for decades for his great and enhanced chemical sensitivity. And just to give you two examples of the effect of the chemical environment on a double core hole, it's interesting to compare with the single core hole. So if we take here these two molecules, we have the acetylene and the ethylene. So we have the carbon edge, which is experiencing similar chemical environment in these two molecules. And the shift between the primary peak in the acetylene with the ethylene in a double core hole spectra of each one is of around 2 electron volts, where in the single core hole, this shift in this primary peaks is of half electron volts. And if we do a more dramatic change of chemical environment, like if we compare the carbon monoxide, the carbon edge on the carbon monoxide with the carbon edge on the methane molecule, we see that the difference now on the carbon edge, the primary peak on the carbon edge for these two molecules is of 15 electron volts in the single site double core hole and 5 electron volts in a single site double core hole. So this chemical sensitivity to the double core hole makes it a very interesting tool, a spectroscopy tool to, for example, study dynamics and in molecules, of course. But there is a problem. The other side is that small cross sections make it extremely difficult to observe experimentally. That's why it is a process which is known for many decades, but no one, I mean, people didn't give much attention to it in the past. But now, however, with the advent of the new generation of synchrotron and free electron lasers, new experiments are coming to the literature in the recent years. We have recent pre-edge and post-edge experiments being reported in the past years with very nice resolution, and it's just getting better with time. So I think that perhaps is a good time to some theoreticians invest some time in developing methods to this type of spectroscopy. So that's what I'm doing as part of my postdoc here at DTU. So I will just show you some interesting facts regarding the two regions, the post-edge and the pre-edge. Starting with the post-edge, which we also call K-2, which you have here, like in this diagram, you have the photon with the characteristic and necessary energy to ionize 2 electrons in the same atom. So that's the single side double core. And as a result, we have the immediate, we would expect, since we remove 2 electrons from the core, we have the orbital relaxation or orbital shrinking, which basically is to say that the electronic density is being drained towards the double core. Okay, but the interesting about the double core, the K-2 spectra, is that the shake-up satellites, they're very important to the double core hole spectra, where in the single core hole, for example, the satellite peaks, they contribute to medium to small intensity peaks. And in the double core hole, they are as important as the primary peaks. And these shake-up satellites, they are of, you can represent it like this. So the K-2 means that you move 2 electrons from the core, and V to V prime means that is an excitation, Valeriu excitation. And they are driven by the back relaxation, because that's what happens. So because since the beginning, you have the relaxation, and then you have the shake-up induced back relaxation, which means that you are taking the electronic density back to the neighbor atom. And this is to recover, because the shake-up states, they get intensity by recovering some sort of ground state density distribution. So this is a kind of reestablish the balance which was affected by the relaxation or the shrinking of the orbitals. So this back relaxation will be clear in the few slides when I show my actual results, and I will show the orbitals. This will be clear. But for now, we can see that this type of process is a bit exotic, and also you can see that electronic relaxation and dynamic correlation, they play a crucial role. And I mean, it is a bit difficult to work with orthogonal orbitals. That's of primary importance to work with non-orthogonal orbitals. That means the ground state orbitals and the double core state should be represented by different set of orbitals. Okay, and about the pre-edge, so it can be considered as a super satellite. You can think of a super satellite of the K-1 spectrum. And we will have these two distinct channels on the pre-edge region. So the direct, which is a monopolar transition, and the conjugate channel, which is a dipolar transition. That is to say that first you have the dipole induced ionization in the direct channel, and you have a monopole shake-up excitation. This is the direct channel. And the conjugate channel you have now is the dipole induced excitation of the core and a monopolar shake-off or a monopolar excitation on the other core. So these are different channels, and they should be taken into account if you want to simulate the pre-edge double core hole. Okay, and now we'll just mention briefly the approximations that I use for these two regions of the spectrum, starting with the K-2, which is somehow the easiest one to compute, because we make it just an analogy with the Dyson orbital formulation of the photoelectron spectra. Like when people study photoelectron spectra, it's usual that people consider these integrals with the continuum. So the interaction of the continuum, the dipole integral of the continuum with the bound orbitals to be a constant terms when you have high kinetic energy. And then you take the intensity of the peak in this Dyson formulation as the square norm of the Dyson orbital. And Dyson orbital is somehow of a correlated orbital. I will show it later. But for now, for the double core hole, we make this analogy, and we take the square of the simplified two-particle Dyson function, which we have this type of overlap. So we have the final wave function with n-2, which is the double core. And we apply the annihilate operators on the 1s orbitals of the initial state, which is the ground state generally. The other the annihilate operating in other orbitals will give negligible intensity, since you have a double core in one side. So to have a decent overlap, you should have a double core on the other side as well. So this is a monopolar approximation. This is now it is connected. I can just make the connection with the back relaxation when I said that the shake-up state, they get intensity by recovering some ground state distribution, because this is an overlap between the ground state, the initial state, with the double core satellite. So as more similar, as more overlap you have between these two wave functions, more intensity, more intense this peak will be. Okay, but now jumping to the pre-edge region, it is a different approximation. Now we use the continuum orbitals, the continuum wave functions. So we have one electron in the continuum. This electron in the continuum, we use the B-spline, the linear combination of B-spline with the program developed and maintained by Pierre de Cleve in Lund University, which is my collaborator in this project. Pierre will give a talk in 2 days here, I think it's Thursday, and he will present and give you a good overview of his method. So I'm not giving any more mention to this B-spline approximation, just to say that in the dipole matrix elements here in the single channel approximation. So we have the dipole connecting, the dipole operator connecting the one particle dison with this continuum wave function, the photoelectron. And plus we have here the overlap between the continuum with the two particle dison orbital, which normally when people do photoionization or valence state, for instance, it is, people can disregard or ignore the second term because it would be not much important. But for the double core hole, at the particular kinetic energy, it happens that this term here is as important as the direct term, the first one. So you cannot just ignore it. And here are the structure of the dison, the one particle dison orbital, and the two particle conjugate dison, which is this two particle dison matrix contracted with the one electron integrals. And the computation, just to finish, I used multi-reference, HISA CF, and further improved with the perturbation of the second order, the HISA-52, with open MOCAs, where I implement all my relevant matrix elements. And the double core hole, they are computed with this highly excited state and double excited state functionality already available in open MOCAs. And the ground state or any initial state you want is computed separately. So I will have two sets of non-orthogonal orbitals, which we can be orthogonalized with the state interaction approximation also available in open MOCAs. And molecules, of course, molecules with the equivalent atoms, we localize the core with the Cholesky localization procedure. You have the reference for the CVS and the Rice state interaction approximations here. So this is the first result I want to show. This is the water. And this is the approximation, only use the direct term, which is the dipole integral with the continuum and the one particle dison. And you see, since you have the monopolar excitations, so only the state A1 is allowed. So you see here the B1 and B2, the yellow and purple, they have zero intensities as we would expect. But if we see now, if you look at the direct, like here on my right, the direct plus the conjugate, so this is the full approximation, we see now the B2, the B1 and the B2 terms contributing to the spectra now. And we see a really nice and decent agreement with the experiment, which is a recent experiment, by the way. And we see that the green, which is the A1 is one of the channels for the direct, but also has conjugate contribution. So you see here the inclusion of two peaks on the A1 state. So with the addition of the conjugate, we have a better agreement with the experiment. So this is really important to this type of spectral region. And now I jump to the K-2, which here, for instance, in the water around this region, 1,170 electron volts, we have the double ionization potential when the two electrons are actually removed. And from this point, we use this kind of sudden approximation with those two particle dison. And this is the water spectrum. And unfortunately, the experiment is not going high in energy enough. So we could see these shake-up peaks here, which are rather intense. But that's okay, we have the nitrogen. And now it's interesting to see the nitrogen, the effect of this back relaxation. So let me just show you here. The first peak is the primary peak, which is basically mainly contributing the two electrons removed from the 1s nitrogen. And here on the picture, I'm marking this nitrogen, which we create the double core with a star. So you see on the bounded orbitals here, this is the sigma 2s, the pi, and the sigma valence orbitals. And you see the relaxation effect brings the electronic density more localized to the atom which we created the double core hole. So we have the draining of electronic density towards that direction. And the second peak here, this rather intense peak on the nitrogen spectra, it is a shake-up when you have the excitation, the double core plus an excitation from the pi to a pi star. And when we look at the orbitals involved in this transition, you see that the pi and the pi star is going, the electronic density is directed to the opposite direction. And you see here clearly that you have the electronic density more localized on the neighbor atom. And the same we see with the sigma. So the sigma valence is more localized on the hole, and the sigma star, the electronic density moves towards the other atom. So when you do this type of transition, So it's kind of sending electronic density back to the neighbor atom and kind of recovering the ground state electronic structure. And also in the CO, here is carbon monoxide on the oxygen edge. And here we see a similar picture when we have the sigma 2s and the pi and the sigma valence orbitals, and how they are localized on the oxygen, which we created the double core. And the pi star, the first pi star, the electronic density is moved to the other direction. So to recover some distribution, so balanced distribution to resemble the ground state density. And that's the reason that in the carbon monoxide edge, double core whole spectrum, you have some peaks here, which you don't see so much intensity because you have the involvement of the sigma to pi star, but the pi star excitation here is the most effective one, as we can see on the picture, to move electronic density to back relax the double core to perform this back relaxation. And as a result, it gets some intensity on the spectra. And in the carbon edge on the other side, yeah, and you see a similar behavior, like we have the electronic density, now the coherent is on the carbon, and the pi star, you have a little more electronic density distributed to the oxygen. So it's kind of, the second peak is of relative intensity is also a pi star. And here, high energy, you have sigma to sigma star. And always in all of this case, you have this type of back relaxation in the shake-up states involved in the double core hole with some reasonable intensity, right? So the second round of example of the K-2 is this series of C2. So we go from acetylene to ethane, and the acetylene is isoelectronic with the nitrogen, the N2 molecule. So the spectra has the same characteristic. First, the intense primary peak, and then you have following this medium intensity, this peak, which is a satellite involving the pi to the pi star. And you see the difference between the ethylene between acetylene and ethylene is that both of them, they have pi orbitals. So in both of them, you see this shake-up, intense shake-up pi star. And when we look at the ethylene, the ethane, we don't have any pi orbitals, so we don't have so much strong intensity here. You only have some sigma star, weak intensities here. But it's interesting to notice between these two guys, they have, as I said at the beginning, similar chemical environments. And in one case to the other, you have this bond distance is elongating a little bit. But if we follow the shift or the movement of the second peak, in one case and the other, which is collected here on this picture, from the blue to the green, we have a delocation, we have a redshift, I could say, of 5.3 electron volts. The experiment shows C electron volts, and we are rather close to the experiment. But it's interesting to say that this kind of effect with such a small exchange of chemical environment is actually stimulates us to apply the study to some sort of application based on ultraviolet pump, X-ray double core hole probe, some kind of dynamics effect or transient dynamics effect on the double core hole spectra. I'm not aware of any experimental theoretical study of this type, so I think that could be a good idea to simulate it theoretically and maybe tell the experimentalists like, yeah, this is a good idea, it's maybe worth a try or not, let's see. And to summarize, thanks to the HAS-SCF, the multi-reference, and the HAS-PT2 connected to the state interaction, which I can use bi-orthogonalized set of orbitals, we were able to compute appropriate and relevant ground state and final double core states and spectral strength, thanks to all the machinery available in OpenMOCAS. And that's it. I would like to thank my supervisor, Sonia Coriani, Piero De Clever, which is working with me on this project, and the Attochem short-term scientific mission that I used to spend a month in Trieste a few months ago where part of this project was developed, and my grant for my postdoc from the Marie Curie program. And that's it. Thank you so much.
Okay, thank you very much, Bruno, for a really interesting talk. Okay, the session is open for discussion. Oh, we already have a question. Professor Kuleff, go ahead.
Yeah, thanks, Bruno. I just wanted to ask, because I looking at your spectra for, let's say, water, what you showed, and also in the CO case, usually in the main peak, you have some shoulders in the experimental data, which you don't have, you don't reproduce. Why you think?
You're talking about this?
Yeah, for example, here. Let's
okay.
see here. So if you look in the left, you have clear shoulder. Yeah, in the main peak. We're talking about the main peak.
The water. Okay.
Yes.
Here.
Yeah. No, the shoulder of the main peak. So you have something which you have A marked on top, and then you have something which goes on the right, and it's like a shoulder of the main peak. So it's clearly
here?
You have a second. Yes, you have even a second one on down, and you have probably something also on the left. And in the down spectrum, again, you have something which is, it's not an experimental noise. I mean, it's clearly something which usually every spectroscopist will say it's a shoulder, it's a state, it's something. What do you think is missing in your way of treating this, that you cannot reproduce such kind of effects in the spectrum?
For sure, this was okay. For sure, there are some effects that I'm not taking into account. For example, I'm doing the calculations only using the ground state geometry, and my plan now is to involve a little bit and compute some potential energy surfaces and get some vibrational resolution for those spectra. And for sure, I will have some more, because from the spectra, for instance, here, I could see there are some vibrational things involved, which I'm totally not taking into account now. This is just to show, because this is a implementation of the method, and now I aiming at use this method to apply in dynamics and vibrational package, and I have a lot of plans to follow with this, of course.
Okay, yeah, thank you.
Okay, thank you. Any more questions for Bruno? Okay. I have to say that I totally agree. This might be a vibrational structure, actually, of the bond. So it's only on a single geometry, ground state minimum, I suppose. Yeah, this is just to show that the main or characteristic of the spectra is reproduced, but now it can be polished with more sophisticated vibrational inclusion on the spectra, for sure. Yeah, I mean, you could easily do that just by nuclear ensemble approach, for example. You just generate. Yeah, for sure. Sure. Yeah. But it's pretty good agreement with the experiment regarding the position. But also I guess it is as I can see the experiment. Considering because it's double core, you have, for instance, for the oxygen, something higher than 1000 electron volts is something difficult to see this. But sorry, you shifted the spectra, right? Well, there is a little shift, like in the nitrogen 0.1 EV and 0.8. The water, there is a question mark, because there is a debate, because the experiment here is an old experiment, so they didn't have a reference, so they shipped the experiment with the previous theoretical calculation, which I believe is not accurate enough. So that is a question mark. It's a mess. Okay, we have some question in the chat from Sonia Coriani. Okay. Or it's a comment. The spectra are very noisy too. It is not entirely clear what is shoulder and what is noise. Okay. Yeah, Sonia is my supervisor, so she's just making a comment on the. No, it's a comment. Yeah, this is basically the answer to Professor Kuleff's. Okay. Okay, if there are no more questions for Bruno, then Bruno, thank you once again for your talk, and proceed to our last invited speaker in this session, which will be Professor Françoise Remacle, from the University of Liège, and she will give us a talk titled Exploiting Electronic Coherences for Steering Selective Bond Formation in Molecules Pumped by Ultrashort Optical Pulses. Okay, Professor Remacle, the stage is yours.
Yes, thank you very much. Do you see my screen? Yeah, full screen.
Yes.
Fine.
And
yeah, okay. So, and thank you also for the invitation to talk today. So before I start, I want to thank my co-workers so that if I am short of time, I did it. So I will report on the work of Alessio Valentini, Caio Gonçalves, Stéphane van den Wilderberg, and Martin Blavier in Liège, and we strongly collaborate on this subject of trying to control nuclear motion by exploiting electronic coherence that are created at the step of excitation of the molecule with a very short pulse. In this subject, we closely collaborate with Rafael Levin and Ksenia Komarova at the Hebrew University of Jerusalem. And so I am not sure how much I need this slide, because in many ways my talk is very complementary to the one given by Alex Kuleff at the beginning of this session. So we are interested in using short, few femtosecond, very few femtosecond, 1 or 2 or attosecond pulses to photoexcite or to photoionize molecules. Here I have an example of photoexcitation, because since they are quite short, they have a broad energy bandwidth, and then they allow to build superposition of electronic state at the step of excitation. And as already been alluded to in a previous talk, one can control the nature of the states that are present in the superposition by tuning the parameters of the pulse, the carrier frequency, the polarization, the carrier envelope phase, and also the duration of the pulse. And by tuning these parameters, it is possible to include Rydberg state, valence state, charge transfer state, if they have gained some oscillator strength, in the initial superposition of state, and then to control the nature of the coherence that are built by the optical excitation, trying to then control the nuclear motion. And I will discuss 2 examples that we studied recently in my group. The example of the bond formation in a 4-carbon ring closure in the photoisomerization of norbornadiene, which is a system with a rigid 4-carbon bridge here and 2 ethylene moiety, which upon photoexcitation with a deep UV short pulse, this is what I will show, photoisomerize to quadricyclane. So in general, you need a UV pulse, but what I want to show is that using a specific UV pulse, we can build an electronic coherence which favors the yield in quadricyclane at short time. And the other example is in a cation. We studied the ultrafast Jahn-Teller rearrangement in the methane cation that can be induced by a sudden ionization. And I will report on 2 types of sudden ionization: photoionization with an XUV pulse or strong field ionization. And what I will show is that electronic coherences play a very important role in the strong isotope effect that is occurring in this ultrafast Jahn-Teller rearrangement. And our results are in agreement with pioneering experiment of John Marangos almost 15 years ago now, that shows that using high harmonic spectroscopy, it is possible to experimentally, and this was shown before theory actually, that there is a very strong isotope effect in this structural rearrangement. And so I think after the talks of this session, I don't need to convince you that attochemistry is really qualitatively different from the kind of dynamics that we can induce using photoexcitation or photoionization with longer pulse. And the main reason is that we are building a superposition of several electronic states. And so we are creating a non-equilibrium electronic amplitude state, a superposition of state with a definite phase relation between the different electronic state in several nuclear dimensions. This is what is created in the Franck-Condon region when we photo-excite the system with a short pulse. This is a cut here in the several electronic state in the Nord-Bernardin case. And this superposition of electronic state is then remodeled and reshaped and changed by the non-adiabatic interaction that occurs as the nuclei start to move. And like many others, the question that we ask is, can we exploit the non-equilibrium amplitudes that are created at the excitation step, together with the fact that we have a network of non-adiabatic interaction that will change the coherence we have created, and as Alex Kuleff said, also create new one as the dynamics is going through. I will also show an example of that. And can we exploit all of this to control the motion of the nuclei to specific product? So the fact that we want to use electronic coherence calls for trying to implement fully quantum dynamical simulation. And of course, right now, with present-day computers, it is not possible in a medium-sized polyatomic molecules. So the approach that we took is to do full quantum dynamics, but in a reduced number of nuclear and electronic degrees of freedom. In the case of Nord-Bernardin, we selected 3 nuclear coordinates that are the ones that are involved in the ring closure. So when you start from Nord-Bernardin, you need to close the bending angle, you need to elongate the ethylene bond so that you go to the 4-carbon ring that is shown here. So we included the CC bending, the ethylene, a coordinate that described the ethylene stretching, and also a distortion of the nuclear geometry that takes us out of actually of the C2V symmetry, so that we can describe correctly the non-adiabatic coupling, the very important one that is taking place between the ground state and the first excited state, but also several other non-adiabatic couplings, seam and conical intersection between higher state. And so in the simulation, it means that we are freezing the carbon bridge here, and only the 4 carbon and the 4 hydrogen are allowed to move on our grid. We also need, of course, to truncate the electronic structure. So we describe the electronic structure actually in the Born-Oppenheimer approximation. We compute all the excited electronic state, the potential, and then we compute the coupling between these adiabatic states, that is the transition dipoles and the NAC. And so we do so using the Open MolCAS program. It's a state average CAS SCF approach with 14 states in the state average procedure, so that we get the 8 lower states reasonably accurately. And we compute a very large basis set because we need both valence and Rydberg state, and we need to get the correct changes between valence state and Rydberg states when the photoisomerization occurs. And we compute those for 65,000 grid points in these 3 nuclear coordinates. And here you see the role of the phi distortion, because if phi is 0, we completely miss in our system of coordinate the S0, S1 conical intersection, while as soon that we have a finite value of phi, we can describe correctly the conical intersection. Using this level of electronic structure, we get a reasonable UV visible spectrum, which is in good agreement with the one that we found reported in the literature. So we implement a solution of the time-dependent Schrödinger equation on this 3-dimensional grid for 8 nuclear degrees for 8 electronic states, sorry. We need actually many more grid points than the one that we compute, because we also need to extrapolate on the border of the grid, which means in the end we have about 4 million complex amplitude to follow by solving the time-dependent Schrödinger equation. In the Hamiltonian that is here written on the grid, we include the coupling to the pulse in the dipole approximation, and here is the term for the non-adiabatic coupling. And the dipole, the pulse are short, so the electric field is defined as the derivative of the vector potential. So computationally, what we did to gain some computer time is that we are using a finite difference algorithm to describe the non-local kinetic energy and momentum operator on the grid. And we have tested this method of integration and benchmark it compared to the Fourier transform approach. And we get very good accuracy, and it saves us really a large amount of computational time. So what I would like to show before showing the results that correspond to a superposition of several electronic states that is built by the photoexcitation by a deep UV few femtosecond pulse, I want to show the situation that is occurring if you photoexcite the system with a longer pulse, and so you would selectively access the S1 state. So we then have an initial state that is non-stationary with respect to the nuclear motion, but that the state evolves on the S1 here. And as when it will reach the region of the conical intersection, we are going to transfer amplitude and therefore population on the ground state here on S0. And some fraction of the wave packet will go back to Nord-Bernardin, and another fraction will evolve to quadricyclane. And at the place, in the region of the conical intersection, we create an electronic coherence because of this non-adiabatic interaction. I guess I need to launch the movie, not to have a pointer. So I think I should go like this. No. So I have a movie showing it, but I don't appear to succeed. Ah, yeah, here, to launch it. So you see the wave packet in 3D moving on S1, and it was a lot of work of Alessio to visualize in 3D. Then you have population here, coherence here, and you see the coherence vanishes when the wave packet do not overlap. This is what people called decoherence, but you see that it revives after about 50 femtoseconds when the wave packet here is revisiting the region of the conical intersection. And so there is really a complex dynamics that can be created, electronic dynamics, by the time evolution of the wave packets on several electronic states. So what we did, because we want to favor the formation of quadricyclane, and so we understood, and it was shown by previous works, that what is very important to control the yield is to the position at which the wave packet arrived around the conical intersection. And so what we did is to launch the wave packet on S1 on several positions around the conical intersection, and to monitor the yield that we get in Nord-Bernardin and the yield that we get in quadricyclane. So this is a very busy slide that shows the results of these 5 positions. The point is that we have 2 positions that are very interesting for the dynamics, the position 4 and the position 5. And so because the position 4 is giving us a high yield, 4 is this azure blue, and so you see a rise here in quadricyclane before we have a rise in Nord-Bernardin, while for 5 we have the typical situation of photochemistry that you have at all times a larger yield in Nord-Bernardin compared to quadricyclane. And so we back integrated these 2 positions to the Franck-Condon region to understand from which state we were starting to arrive at this position here. And we got rather interesting results because the position 4 correspond to a superposition of the S2 and the S3 state in the Franck-Condon region, while the location 5 is actually following S1 all the way to the Franck-Condon region. And then because in the Franck-Condon region, we have optical selection rule because the norbernardine belongs to the C2V group. And S1 belongs to B1, while S2 belongs to A1. We can, by using the polarization of a short linear, linearly polarized UV pulse, we can selectively access either S1, which is the traditional photoexcitation scheme, or access S2, which is bright if we polarize along Z. And S2 is very much coupled already to S3 in the Franck-Condon region. So instantaneously almost, we create this electronic coherence between S2 and S3, which gives us here a higher yield in, and this is also shown here, in quadricyclane at short time. So by exploiting by controlling the polarization of the pulse and by orienting the molecules, but norbernardine has a permanent dipole moment, so could be oriented, we can really define two different paths in the configuration space of nuclear and electronic degrees of freedom. If we use a polarization along X, we have a single excited state path that follows S1, and that will give us a high yield in norbernardine, while if we use a short pulse that is polarized along Z, we create from the beginning, from the step of the excitation, a coherence between S2 and S3 that will evolve to S1 and reach the conical intersection around S1 in a position that is favorable for the formation of quadricyclane. So we run the dynamic in 3D, and these are the results. So these are plots of the populations and the electronic coherence in the 3 nuclear coordinates for the 2 types of excitation. The excitation that access S1 will give us what I essentially showed in my slide with the movie. The wave packet is going to the conical intersection. You create an electronic coherence, and it will revive every 50 femtoseconds when the wave packet on S1 revisit the region of the conical intersection. In the case of the UVZ excitation, which is more interesting from many points of view, we create this electronic coherence between S2 and S3 that will evolve in time and in the geometry space, will lead to a coherence between S2 and S1 and will bring us at the right position in around S1 in the region of the conical intersection to yield to quadricyclane. And so not only do we get different paths in for the 2 types of excitation, but we also get very different electronic dynamics between the old and the new bonds. And this is what I want to show on this slide. So what we are calling the old bonds are shown in red, and this is the bond between the 2 carbons of the ethylene moiety in norbernardine, while the new bonds are the bonds that are formed. So between the 2 carbons that were not linked in the norbernardine form. And so we can compute the amount of electronic density along this bond as the dynamics unfold. And this is actually a quantity that has a term that corresponds to a probability to be present in that bond, but we have also to this kind of population term here we have a term that is reflecting also the coherence between the electronic states that are involved in the dynamics. And the point is that we have a rather monotonic compared to the other situation. We have a kind of monotonic evolution of the density between the old and the new bond, at least at short time. For the UVX pulse, you see that we have a decrease of the density in the ethylene bond and a rise of the density in the bond that are formed, and then we get oscillation, but more or less we start to equilibrate the density. And this is confirmed if we now subtract the density at this time point compared to the densities that we had initially. You see that we have an excess of electronic density at the bottom of the molecule where we want to create the bond. And so here we have a kind of monotonic behavior that follows the determinantal change in the state S1 and S0 as the dynamics unfold. While here we have for the UVZ pulse that creates a superposition of S2 and S3, and so we have an electronic coherence here. You have a very fast oscillation. You have the same first behavior at short time, that electrons are moving from the old bonds to the new bonds, and then we have a charge migration actually between the two kinds of bonds with a period that corresponds to the energy difference between the S2 and the S3 states. And if you look at subtract the density at half periods, you see that first we are bringing electronic density to the new bonds. Now we show the molecule from the bottom. So this is where we want to make the new bonds. And at the next half periods, we have brought back density in the old bonds that is here. And an excess of electron is shown by a green color, which I should have said from the beginning. So in the time that I have left, I would like to report now on our work on the isotope effect in the methane cation. So as I said, this was motivated by an experiment of John Marangos, who showed using high harmonic spectroscopy that there was a very strong isotope effect in the yields of harmonics that was much larger than what you expect on the basis of the effective mass ratio. So this work, experimental result, triggered a large number of theoretical work, and there was a very complete study using MCTDH by Mondal and Varandas, who finally computed the dynamics with all the nuclear degrees of freedom and got a large isotope effect also, but they were not describing the initial state resulting from a process of sudden ionization in detail. They just assume constant ionization efficiency to all the three states of the cation that are shown here. And then there were a study of the photoionization of the ionization yield, by Madsen, that shows that indeed they were the mode that are involved in the Jahn-Teller effect were very important to determine the photoionization yields. And there were also a study of Sergei Pachovsky that were relating the isotope effect to the very different gradient that you have for the three lowest states of the cation at around the TD point when you suddenly ionize from the ground state. So in high harmonic spectroscopy, the process for ionization is a strong field ionization, but we studied two processes, photoionization and also strong field ionization. And these are the potentials that we use. So we have here the ground state, you have the three lowest states of the cation, and here we chose two specific nuclear coordinates. One coordinate that is pointing to the C2V minimum on the ground state of the cation, and one coordinate for the nuclei that is pointing to the D2D local minimum on the ground state of the cation, because there is also an issue to try to understand if when the structural rearrangement occurs, one is passing by the D2D geometry before going to C2V, the D2D being less distorted than the C2V one. So we use here coordinates that are linear combination of Cartesian displacement. This table here shows the coefficient on each of the Cartesian displacements. But the point that I want to make on this slide is that these two coordinates actually sample effectively all the modes of the TD form, but also in the C2V and in the D2D geometry that are involved in the Jahn-Teller effect. And this is very important because, again, we need to reduce dimension because we want to do full quantum dynamics on the grid. So these are the potentials that we get for the three lower states. We use again state average class approximation or for describing the electronic structure. We get good agreement with previous computation, and as in the case of Norbernadain, we solve the time-dependent Schrödinger equation on the grid for these two coordinates and the three lower states of the cation. So I think we are seem to have, yeah. So I will first report on photoionization results. So here we use a sudden approximation to compute the photoionization matrix elements, these D matrix elements here, and they will determine the amplitude on at each grid point for each electronic state of the cation for a given orientation of the pulse that is used for photoionizing the system with respect to the orientation of the molecule. So to compute this photoionization matrix element, we use a single active electron approximation. So essentially we get the Fourier transform of a dipole orbital and it's a dipole matrix element. And the point is we get a Fourier transform because essentially here we are using orthogonalized plane wave to describe the function of the continuum. So you have here the electronic coordinates, orthogonalized plane wave, and here a Dyson orbital, and the Dyson orbitals are here. We compute them for all the geometries that are comprised in the Frank-Condon region. And so this allows us to define the initial amplitude at each grid point that will be weighted by the amplitude of the wave function in the ground vibrational state of the neutral, multiplied by the scalar product between the orientation of the field and the Dyson orbital. And so we can compute like this the yield of ionization for each electronic state as a function of the orientation of the electric field. These are the maps that are shown here. And we did so for two values of the carrier frequency of the XUV pulse, very short, that we use to photoionize. One carrier frequency that is correspond to the 9 harmonic of 800 nanometer IR field. And so we essentially access the GS and D1 and very little of D2, and one higher carrier frequency where we access the 3 electronic state in more or less equal amount. So this is the localization of the initial state on the grid on the 3 electronic state for CH4 plus and for CD4 plus, because in the end we want to analyze an isotope effect. We don't have a very big difference between the two isotopomers, and the reason is that the only difference would be in the delocalization, let's say this way, of the ground vibrational state of the neutral, which is tighter in the case of CD4 than in CH4. So we have a slightly less extended Frank-Condon region in the case of the CD4 molecule. In terms of looking how the state is localized on the different electronic state, you see indeed that we get more population, and so in the case of the higher carrier frequency for the ionizing pulse. And if we look now, if there is a preference for C2V or for D2D, you see that on the GS, we clearly have a localization of the initial state that is more favorable for moving to the C2V minimum. It's more or less isotropic for D1, and we clearly bias in the direction of D2D for the D2 state. Next, we, I don't know what this is. Yes, okay. Next, we look at the dynamics. Is it still okay? You still see my slide?
Yes, we see your slides, but we also see some comments.
Something is strange. Yeah. Wait, I think I need to share screen again.
Yeah,
Is it, yeah, I activated something that I don't know.
Yes. It looks like that someone is listening to you and typing what you say.
No, it's like I activated Siri or something. No, it's not.
Something like that.
So I don't know what I activated. I'm sorry. Okay, I will continue because we will waste too much time. I think.
Take your time.
I really don't know how to deactivate this. Should I stop sharing and share again? Can I?
You can try. You can try. I don't know if it will be helpful, but
no, it doesn't. It is not useful at all.
Yeah. Okay.
I'm sorry. I pressed a button, but I have no idea what.
Don't worry. No problem. You can proceed with subtitles.
Yeah, let me proceed. Right.
If you don't mind.
I don't mind. So share. Yeah. So I wanted first to comment on the population dynamics. So these are the low carrier frequency that only access GS and D1, while here there is the results of the population dynamics for the larger carrier frequency that accessed also D2. And so you have in full line the CH4 plus and in dashes CD4 plus. And so what you see is that we have a very different dynamics when we access the D2 state with a lot of population transfer between the states and oscillations. And since we have a different mass for the nuclear motion in the CD4 plus, we also have different period for the oscillation and a strong isotope effect in the population dynamics, which we do not have in the case of the photoionization with the lower carrier frequency pulse. We also see now, if we monitor the amount of population around the D2D minimum, that we are getting first a population of D2D and then a population of C2V in green, that the population in the D2D occurs very fast, right? In the first 2-3 femtosecond for CH4 and a little later in the first 7 femtosecond for CD4. Not a lot of differences between the two carrier frequencies. The next slide that I want to show is to show the computation of the autocorrelation function of the initial state. So here you have in dots CD4 and in full lines CH4, in orange for the high carrier frequency pulse, and in violet for the lower carrier frequency pulse. So you see, as expected, that it takes more time in the CD4 a cation to go out of the region populated initially, which makes sense again on the basis of the effect of the difference of masses. But now if we look at the ratio of the autocorrelation function, we see that this ratio behaves very differently for the two carrier frequencies. And if we make a zoom on the very early time dynamics, so between 1 and 1.6 femtosecond, which is the kind of time range that is probed in high harmonic spectroscopy, you see that we get a very different ratio. That if we have an initial state that involves the D2 state, and so we create coherences between D2, D0, and D1, we have a rising ratio that behave in a rather similar way to what was reported experimentally. We reach a value of 2.6 at 1.6 femtosecond, while we have a rather constant ratio in the case where we do not access the D2 state. And so we investigated this a little further. So of course, if you look at the expression of the autocorrelation function, and I remind you, we average over the orientation with respect of the electric field with respect to the molecule, we see that we keep a term here that depends on the electronic coherence at the level of this averaging over the ensemble. And we also see from this slide that if we do not include this term in computing the autocorrelation function, our isotope effect is gone, actually. We now have that most of the curves are behaving in the same way, and we reach a ratio about 1.5, 1.6 at about 1.6 femtosecond. We also see here the localization of the electronic coherence D2, D0. Again, it is the ensemble electronic coherence at the early time dynamics. And you see that, as one expects, right, we have a fast dynamics in the case of CH4+, and a very slow dynamics because it takes more time to go out of the Frank-Condon region for the CD4+ cation. And we have observed similar effect of the electronic coherence on the non-adiabatic coupling in other systems in N2 and in LIH. And what is happening here is really the interplay between this electronic coherence and the strong non-adiabatic coupling that occurs right away at the step of excitation, because the Jahn-Teller effect takes place in the middle of the Frank-Condon region. So
excuse me, Professor. Excuse me for interrupting you.
Yeah.
You have 2-3 more minutes, if
yes.
it's okay.
That's fine. I am done.
So sorry for interrupting. Thank you.
And so now I will not talk too much about this work because Martin Blavier will present a poster on this work on Friday. So we did a similar work now to look at the effect of a strong field ionization. And so we computed the probability to have a strong field ionization as a function of grid point and as a function of the orientation of the electric field. And the bottom line is that we also recover a strong isotope effect when the D2 state is accessed by the process of ionization. And again, we can show that it is an effect of the interplay between the electronic coherence and the non-adiabatic coupling. So I am essentially done. I wanted to show 2 examples where electronic coherence play an important role in connection with non-adiabatic coupling to steer nuclear motion in norbornadiene and in the structural rearrangement of the methane cation. We showed that we can also control nuclear motion with electronic coherence that are built by using different value of the carrier envelope phase in the LIH molecules. And so I think that it is very important now in atochemistry to learn how to synthesize electronic coherence and to exploit them, and that they are not dephasing instantly, as was also shown in previous talk. And then we need to understand the interplay between this electronic coherence and the non-adiabatic interactions that occurs after the excitation so that we can control the motion to the product. So thank you very much.
Thank you very much, Professor Remacle, for a really nice talk and interesting. I have to comment that it is really beautiful when you do wave packet dynamics in 2 or 3D, and then you can visualize your full wave packet.
It's very difficult in 3D, actually. We spend a lot of time to understand.
Yeah, I can imagine.
Yeah.
Okay, we have one question in the chat. So Stefanos Karlstrom asks, how demanding are the full quantum calculations?
They were quite demanding, especially in norbornadiene because of this 3D nuclear grid, right? And so I don't know what kind of estimate is expected, but also because we include the effect of the pulse, right? So the photoexcitation by the pulse, and this is also slowing down the dynamics considerably. After the pulse, it goes a little faster.
Yeah, okay. I suppose you have to use extremely short propagation step because your pulse.
We need to use very short, so it is typically even smaller than an atomic unit.
Oh, okay.
Okay, because during
it's really
important. After the pulse, one can restart dynamics and use a somewhat longer time step. But all of this is always very, very involved, right? To do it right. Yes.
Thank you.
If I may comment, probably it's not the way to continue on a grid in multi-dimensions, right? It's obvious.
Okay, for 3D, grid is more than good. It is easily implemented.
Yeah.
We have one more question for Morgane. Go ahead, Morgane.
Yes. Hi, Françoise. Thank you for the talk and the nice results. I had a question about the first part of your presentation.
Yes.
Maybe a stupid question, but it is a clever idea to start in different places around the conical sections and check which one then gives you, and then you back propagate. Stupid question, but in many dimensions, how do you ensure that you will pass by different quantum points exactly?
We somehow went back to the Frank quantum. It was not clear, but we knew we want to go in the direction of norbornadiene.
Yes.
Okay, and so this we could ensure that we don't want to push momentum in the direction of quadricyclane. This we could ensure. But indeed, there were no guaranteed we are going to arrive right at the Frank quantum point. Of course, no.
Okay.
But I don't remember fully the detail, and Alessio is not here to say something, but we arrived close enough that we next understood that if we photoexcite selectively S1, it will work, and if we photoexcite S2 that is coupled to S3, it will also work.
Okay.
But you are right, we have no guarantee, and indeed at the beginning we were going the opposite direction when we started. Yeah.
Okay. Thank you.
Yeah.
Okay. Thank you once more, Professor Remacle, for accepting to give a talk on our symposium. And with this talk, we came to an end of today's afternoon session. And I would like to thank once more to all speakers in this session for participating in YSS. And now, according to schedule, we have a poster session. Okay, so the poster session, as Gabriele briefly informed us in the morning session, will be held in the way that each poster presenter will here in this room, in this Zoom room, which we call plenary room, will present his or her poster in 5 minutes. And they will do it one by one without any discussion in between. And then afterwards, after all of them are done, each of them will be transferred to the breakout room, which you can find in the lower part of your Zoom screen. So where you have a shared screen, and then in the right part you have breakout rooms. You can click on it and you can see we should have like 6 rooms. So room 1 with the name of the poster presenter, room 2 with the other name, and so on. Anyways, after the presentations here in the plenary room, each of presenters will be transferred to his or hers breakout room, and then all of us can join to any room we wish, any breakout room, depending on which poster we are interested in. When we enter some breakout room, we can discuss with the poster author, poster presenter in that room, and then we can go back to the plenary room when we want, when we are enough of that poster presenter. Kidding. And then from the plenary room we can go to some other breakout room. Okay, if you have any questions, feel free to raise your hand and to ask us. All the time during the poster session, one of us, or maybe several of us, will be in the plenary room all the time. So if you get lost somehow, or if you need any sort of help. Okay, so I think, I hope that I have been clear and that we can actually start with our poster session, at least with this first part, in which the poster presenters will present in 5-minute talk their posters. Okay, so the first presenter will be Dr. Valeriu Scutelnic. Again, I apologize if I mispronounced the name, from UC Berkeley, and he will give us a poster presentation titled X-ray transient absorption reveals the 1AU and pi star state of pyrazine in electronic relaxation. Valeri, are you here? Hello.
Yes. Can you hear me?
Yes, yes.
Right. Thank you.
Go ahead.
All right.
The stage is yours.
So, yeah, thank you very much. And first of all, I would like to thank the organizers for this fantastic opportunity to present our work on electronic relaxation of pyrazine. So pyrazine is a small molecule. It's a heterocycle, but it's well known for its strong byronic coupling that mediates the relaxation from the S2 to S1 state. And photoelectron spectroscopy found that this relaxation happens in around 20 femtoseconds or so, and then in 15 picoseconds, this S1 state would decay much slower to the ground state. Now, we want to focus on transitions that involve the carbon core and the valence orbitals. So for that, we require production of the soft X-rays. And that we do with our tabletop setup that basically produces the infrared pulses with an OPA system that is derived, so part of the energy is derived from a high power amplifier. And then we produce these infrared pulses with a topaz system, and then the infrared pulses are focused into the helium gas target that are propagating through the vacuum of our setup. And then we block the infrared light with a metallic filter. Then these harmonics, we are focusing with a toroidal mirror into the sample cell, where the interaction with the pyrazine gas phase molecules is happening. And then we disperse this light with a grating and project the photons on a CCD camera. So in this way, we can reconstruct an absorption spectrum of our sample. But before the X-ray pulse arrives in the sample cell, we excite the molecules with an ultraviolet pulse. And just varying the time delay between the two pulses, you can reconstruct the entire dynamics, and the the X-ray photons that have been absorbed are carrying the information about the dynamics that happened. the pyrazine. So here on the left, we have the ground state absorption of pyrazine. On the horizontal axis, you see the photon energy. On the vertical axis is the absorbance. And the most intense line here, you can assign right away to 1s to the pi star transitions. And the other bands are actually Rydberg transitions. So if you add the ultraviolet pump pulse before the X-rays, you can collect this map. On the map, we have on the horizontal axis, again, the photon energy, same scale as above. And on the vertical axis, we have the delay between the pump and the probe. The color represents the difference in absorption in the cycle with the pump and without. So bright red color means that there's more absorption in the excited state, and the more bluish color is when there's less absorption induced by the ultraviolet pulse. So you can already identify here that there are these negative signals which we assign to the ground state bleach. But importantly, we observe new features in the pre-edge range, so in the background free range here, below the 285 electron volts. And we can identify 3 different transients happening in the dynamics of pyrazine. Definitely, it's more than what has been proposed so far. So we identify in this dynamics that there is also the participation of the dark state, 1AU state. So for more details of how we are doing this assignment, please visit my poster number 1. Thank you.
Thank you very much, Valeri. We go to our next poster presenter, which will be Mr. Gaurav Pandey from the Indian Institute of Science, Education and Research. And he will present to us poster titled Classical Description of Molecular Attoclock to Simulate Coupled Electron-Nuclear Dynamics of H2 Molecule.
Okay, so can you hear me and can you see my, okay,
yes.
Thank you.
Yes.
So thank you for the kind introduction. So we have studied the sequential double ionization and dissociation dynamics of hydrogen molecule. In our simulation, this hydrogen molecule is exposed to intense ultra-short elliptically polarized laser pulse. In sequential ionization, the first electron ionizes at early times, and after some time delay, say delta t, the second electron ionizes, and finally the molecular ion explode and produce the 2 protons. So we applied the molecular clock technique to trace the propagation of wave packet between these 2 ionization steps. In a molecular clock, 2 clock hands are required, one for the nuclear motion and other for the electronic motion. So in this study, we took kinetic energy release, KER as the clock hand for the nuclear motion, and relative emission angle of electrons as a clock hand for the electronic motion. So to study this coupled electron-nuclear dynamics, we followed a quasi-classical approach. In this quasi-classical approach, I solved this classical Hamilton equation of motion in presence of laser electric field. The total Hamiltonian of the system is given by this expression. You can see this first part is simply the sum of kinetic energy and the potential energy part, and rest of the terms are the repulsive auxiliary potential, which mimics the Heisenberg uncertainty principle. So this repulsive potential stabilizes the molecular system against the pre-dissociation and auto-ionization. So as I have said that in molecular clock, we have 2 clock hands, so one KER and the relative emission angle. So this is the correlation plot of these 2 clock hands. We can see that in a majority of the double ionization event, both the electrons emit in the same hemisphere. With a relative emission angle around 0 degree. So, and this is because the value of the time delay delta t. So if the value of time delay delta t is an even multiple of a half optical cycle, then electron emit in a parallel direction. And we can see this is the plot of time delay between the two ionization step. So we can see that a majority of the double ionization event occurs with a time delay of around 2.5 femtosecond, which is an even multiple of half optical cycle. And that is why we got the maxima here at 0 degree. So in molecular clock, the time reference is given by the optical cycle or the optical period of the laser pulse. So the angle range from 0 to 180 degree corresponds to the one laser half cycle, which is 1.25 femtosecond. So if we take a smaller slices of this angle range, we can get a finer temporal resolution. So we took the small angle range from 0 to 20 degree in parallel emission and 160 to 180 degree in anti-parallel emission. The temporal resolution corresponding to this angle range is around 140 attosecond. So we have calculated the KER in this temporal in this angle window, and with KER we can easily calculate the internuclear distance, and this is the distribution of internuclear distances. So these distributions simply the attosecond snapshots of the wave packet after the first ionization steps and indicate how the wave packet propagate after the first ionization step towards the larger internuclear distances. So with this, I can conclude that the quasi-classical model we have applied is quite accurate in describing and predicting the light-induced multi-electron processes, and can easily be extended to other multi-electron atoms. So thank you, and for more detailed information, please visit my poster. Thank you.
Thank you, Gaurav. We go on. Our next poster presenter will be Miss Gaia Giovannetti from DESY Hamburg, and she will present as a poster titled "A Tabletop Soft X-ray Beamline for Transient Absorption Experiments in Liquid Phase."
Good afternoon. I'm Gaia Giovannetti, and I am a PhD candidate in the CIVEL-ATO group led by Professor Francesca Caligari in DESY Hamburg. And in this presentation, I will report the development of an attosecond soft X-ray beamline, which combines high harmonic generation with liquid jet molecular source for aqueous phase experiments. And I would like to start saying that transient absorption spectroscopy is a very well established technique that allows for studying relaxation processes in biologically relevant molecules, and in particular, when performed in the water windows of X-ray spectral range, transient absorption allows us to investigate such molecules in their physiological environment, which is the liquid phase, with the advantage of site selectivity. And however, probing the electronic dynamics in valence and core orbitals requires attosecond light pulses, and the novelty of my project lies in the combination of such attosecond soft X pulses with ultrafast UV light. Indeed, our group demonstrated the possibility of generating sub 2 femtoseconds UV light pulses via third harmonic generation in gas. And furthermore, in the context of probing ultrafast electronic dynamics beyond the gas phase, liquid jet sources recently revealed to be an exceptional tool to perform ultrafast pump probe spectroscopy in liquid phase. From an optical point of view, the generation of isolated attosecond pulses in the soft X spectral range via harmonic generation requires a mid-IR wavelength and carry envelope phase stable driving field. And therefore, our soft X beamline is driven by a 2 stages OPA, which is able to produce few optical cycle, multimillijoule, and CEP stable pulses, which are found to be tunable between 1.3 and 1.8 microns. And furthermore, I would like to introduce the development of our microjet source, which is able to generate stable liquid sheets characterized by submicron thickness, whose thickness is actually tunable from above 1 micron down to 20 nanometers. And the advantage of using microjet sources with respect to conventional transmission cells consists in the fact that jet sources provide rapid sample induction while containing pulse dispersion and sample damaging, which makes these sources extremely compatible with high peak power pulses. And in particular, the aim of my project is the investigation of the ultrafast relaxation processes that take place in metallic complexes in their biological environment. This means in aqueous solution, exploiting the unique properties of both our EV and soft text light. Thank you for your attention. Hope to see you in the dedicated Zoom room.
Thank you very much, Gaia. We go on. Our next presenter will be Mr. Thomas Rook from University College of London. And his poster is titled Influencing Holographic Interference Patterns, Dancing Spiders and Waving Patterns. Thomas, feel free, start your slideshow.
Sorry.
We can hear you.
How do I?
But we still don't see your screen.
My apologies, I'll just be 2 seconds. It seems to have...
Take your time. So it's a green button in the lower part of share
sorry about this.
Don't worry, take your time.
Oh my.
So do you see the green button?
Yeah, it was. I was having trouble with the presentation itself. I'm sorry.
Oh. Okay.
Share screen. Okay, there we go. This.
Okay, great.
Okay,
now we see. Now we see it. Go ahead. The stage is yours.
Which screens can you see now?
Your presentation is not in slide show mode.
Yeah.
This is Mac, right? I'm not familiar with Mac.
No. I think I can. Let me see. Oh, what have I done?
Okay.
How do I?
Okay. Now you exited. Now you exited.
Yeah. Yes, because I've accidentally. Oh my goodness. I'm so sorry.
We have. Take your time.
Is it okay to do the presentation outside of slideshow mode? Because that seems to be.
Yeah, of course.
I'm sorry.
Of course, if it's okay to you.
It's okay. It's not preferable, but it's fine. Okay, where is it? Gone. So sorry.
PowerPoint is a messy thing.
Yeah, it's not even loading now.
So you have local problems with your
Yes,
PC?
this is the issue, I think.
Okay. Then would you?
Yeah, can someone else not try?
Yeah, maybe. Maybe. Don't worry. But if you agree, you can present your poster at the end if you manage to set up.
I think I may have it now. Actually, I'm sorry. But
okay.
Let me just. It's not going to be on presentation mode, but this is fine. I'm happy with this.
Okay.
Let me see. Share screen. This one is okay. Share. Okay, sorry about
Beautiful.
that.
Yeah.
Let me get rid of this.
Yeah. The stage is yours. Enjoy.
That's almost as good as the real thing. But I don't know why I wasn't.
It's fair enough, I would say.
Okay, so thank you for being patient, and thank you for letting me talk. I'll try and be fast because I was wasting a lot of time. I'm going to talk about influencing holographic interference patterns. Firstly, I'll just talk about two different methods. So strong field approximation. So semi-classical action turns out to be like this, which doesn't have any Coulomb included in it. And then we try and include Coulomb interaction, and you have CQSFA, which has where it's you derive the scattering amplitude in the form of a path integral, and you can get the semi-classical action that looks like this, which has got Coulomb interaction in it because well, I mean, here's the Hamiltonian for the combined Coulomb potential and electric field. Next slide. Oh wait, no, actually, I should talk about the orbits that are here. So you can use the saddle point approximation for both of these methods to get the amplitudes in terms of individual quantum orbits. And well, for the Coulomb quantum strong orbit field, quantum orbit strong field approximation, you have the field dress momentum can vary while you're in the continuum, so you're going to have a greater variety of orbits than you would for the direct strong field approximation. So orbits 1 and 2 here for the CQSFA are analogous to the direct SFA orbits, just deflected by the Coulomb potential. Orbit 3 is partially rescattered orbit, and orbit 4 is like a fully rescattered orbit. Okay, let's move on. Here's the expression for a linear bichromatic field. For this sort of field, you can break a few symmetries that you'd have in a monochromatic field, namely a half cycle symmetry, plus you have like two other types of reflection symmetry, like depending on which are around different axes in the real time. The symmetries are linked to each other in the sense that if you have any two of those symmetries, that automatically implies that you'll have the third symmetry in your field. And in a similar sense to that, you have the case where if you've broken half cycle symmetry, like you do for r equals 1, s equals 2, if you have one of those reflection symmetries, that will imply that the other reflection symmetry is maximally broken. And so if you then link, you can find a correspondence between the symmetries and the symmetries of the saddle points. And then for the direct SFA, and then when you have the CQSFA, these symmetries, some of these symmetries are broken. As you can see here, this isn't symmetric around this axis fully, at least. So yeah, there's two different phases. What am I saying? Yeah, this is the Coulomb potential breaks the degeneracy of orbits and this sort of thing. So it's just because they behave differently in the continuum due to the interaction with the Coulomb potential. This, like, you can, I guess, understand this qualitatively if there's like if you so take the monochromatic, take the bichromatic field as a perturbation of, take the path of the monochromatic quantum orbits as a perturbation of the path of the monochromatic quantum orbits, you can understand the changes from monochromatic case to the bichromatic case sort of qualitatively. But even so, like there's still a partial like residual symmetry here that you can kind of make out. Okay, just move on to the last slide because I'm wasting all the time. Okay, so yeah, some features of the holographic patterns might not be like entirely sensitive to the exactness of this symmetry. So such as contrast, and for one of these things would be like, okay. Okay, so for instance, the spider pattern here, you can see this is oscillating back and forward as you verify the relative phase of the the two-color field, and this is because the orbits 2 and 3, which make up the spider holographic pattern, are from the same half cycle, and like in a similar way, the contrast of this one varies as you verify, because orbits 3 and 4 are from different half cycles, originate from the saddles, originate from different half cycles. So, okay, yeah, this can be linked to just the symmetries of the saddle points themselves. But if you then take this and look at the sort of combined interference, sort of coherent superposition of the 1, 2, 3, 4 orbits over a half cycle, you can see the over a full cycle, sorry. You see the prominence of the different holographic patterns varies with phi, and you can sort of relate this to the symmetries of the field. And that's, thank you for listening. I'm sorry about that confusion of that all, but yeah, thanks.
Thank you, Thomas. Don't worry about technical issues. They happen all the time. We have to go on. Our next presenter will be Mr. Edwin Olofsson from Lund University, and his poster is titled Frustrated Tunneling Dynamics in Ultrashort Laser Pulses. Edwin?
Yeah, can you hear me?
Yes, and we see you.
Good.
Go ahead.
Yes, so I will be discussing about frustrated tunneling. So first I'll just describe what frustrated tunneling is. So when you shine with intense laser light on an atom, you not only ionize the atom, but you can also excite it. And the picture in frustrated tunneling is that you start with the atom in the ground state, you shine some light, and that distorts the potential so that the electron can tunnel out. And then it propagates in the combined atom and laser potential, and at the end of the pulse, it can end up in an excited state. So we have used a model based on the strong field and saddle point approximations. So the strong field approximation is just that you consider first normal propagation with the atomic Hamiltonian up to some interaction time where the atom is excited, and then you propagate with the full Hamiltonian to the end of the pulse. And the strong field approximation is just that you consider only the laser potential after the excitation. And you can approximate this time integral with the saddle point approximation, and then you get this tunneling equation that gives you a complex tunneling time that depends on the momentum of the electron. And it was Popyshenko who suggested that you can use the laser-driven trajectories and to calculate the angular momentum and the energy at the end of the pulse, so that you can associate a particular momentum to a given excited state. And we studied this model for few cycle pulses in hydrogen with 800 nanometer light and intensities on the order of 10 to the 14 watts per square centimeter. And we considered the solutions to the modified saddle equations for different N, L, and carrier envelope phase. And we found these that the solutions move on trajectories like this when you vary the angular momentum. So here we have for n is equal to 8, we go the solution starts over here for L is equal to 0, and then it moves along this trajectory to as you go to L is equal to 7. And the same is also So this is for the tunneling time, and the same is also true for this momentum. And then we compared the populations for different quantum numbers in the model with calculations from the time-dependent Schrödinger equation. So here you see for 2 and 3 cycle pulses. And then we varied the carrier envelope phase of the pulse. And then you can see that for the total population for n is equal to 5, for instance, there is some qualitative agreement in the CEP behavior of the population. But when you consider the individual contributions from the different angular momentum channels, then the model does not agree with the TDSE calculations. So here, for instance, you see that L is equal to 0 and L is equal to 1 is dominant for the model, whereas in the TDSE case, you have mostly L is equal to 4 and 3. So if you want to know more, then you can stop by my breakout room.
Okay, thank you very much, Edwin. I would like to thank all poster presentations in this poster session. And now I would like to ask them to go in their breakout room. And then afterwards, we will all follow them particular room. And thank you all for participating in the first day of YSS. And I guess see you tomorrow in 9:30.